Hello. Now we are going to look at how to multiply complex numbers. And in general, our I part is going to be the complication. So I is the square root of -1, which means that I squared, if we square both sides of this equation, I squared would be the same as -1. So when we're multiplying complex numbers, we need to keep track of the fact that if we multiply I by I, we get I squared, and we can redefine that as being -1. Other than that, I will behave basically the same as any other letter that we use in algebra. But we need to keep an eye out for if we get an I squared or a power of I, and what consequences that's going to have because I squared is -1. So if we multiply out this situation here, we have 4 times the complex number 7 minus 3i. Well, we would just multiply that out as normal. So we have a number outside the bracket, that means multiply, so we end up with 4 by 7 is 28, and 4 by -3 would be -12, times I is -12i. They're not like terms, so I can't add them together. That's as far as I can go. So I just behaves like a normal letter, a normal algebraic letter, most of the time. And in this case, that's all it did. This could have been an X instead of an I. It wouldn't have made any difference. But if we end up multiplying I by I, then we have to take into account what we've said about I squared being -1. So if I have I sitting outside my next bracket, I'd multiply this. I have I of 5 units and I of 2i. So I would end up with I times 5i. Sorry, I times 5 is just 5i. And I times 2i would be 2 times I times I. So that would be 2i squared. But I squared is -1 because I is the square root of -1. I squared is -1. So now I need to do that substitution. I need to say I have 5i plus 2 times -1. Anywhere I have an I squared, it's -1. So that ends up being 5i minus 2. And normally we write the real part first. So we would write down -2 plus 5i would be our number. And we can do exactly the same if we have not just I, but something like 4i. So we have multiple of I. So we would just multiply that out as normal. So we'd have 4i times 2 would be 8i. 4i times -7i. Well, now I need to do my numbers first, just like I would in algebra, in normal algebra. 4 times -7 would give me -28. And I times I would give me I squared. And I run into the same problem again. I know that I squared is going to be -1. So I do that substitution. I write out that line. And -1 times -28, well, I'll be left with +28. And I know I write my real part first. So I'm going to say that would be 28 plus 8i. So that is how we multiply that out. And it gets a little bit messier when we have larger brackets to multiply, but the reasoning is exactly the same as it would be for any algebraic brackets. So we just start multiplying out. We have 2 of our second bracket minus 9i of our second bracket. So we just multiply that out as normal. 2 on 3 plus 2i, exactly as we would multiply out a normal algebraic bracket. There is no difference in the structure at all. And then we just multiply out 2 of 3 and 2 of 2i minus 9i of 3 minus 9i of 2i, and we tidy all of that up. So 2 by 3 is 6, 2 by 2i would be 4i, minus 9i times 3, we multiply our numbers first, so minus 9 times 3 would give us minus 27 times I, minus 9i times 2i would be minus 9 times 2 would be minus 18, and I times I would give me I squared. Now most of that is fine. but I see that I have an I squared here, which is going to be minus 1. I can also deal with my like terms. I have 4i and minus 27i. So I can add them up and I get minus 23i. I have minus 18 times minus 1 because I squared is minus 1. So I tidy that up further. I have minus 18 times minus 1 is plus 18. Plus 18. And then I gather up my like terms. I have my real parts here, so I will add them together, and I get 24 in the real minus 23 in the imaginary. And I write my real part first. Now I multiply out just another example of my brackets. So I have 1 of my second bracket minus 3i of my second bracket. So I have 1 of 1 plus 3i minus 3i of 1 plus 3i. And when I multiply that out, I get 1 times 1 is just 1. And 1 plus 3i, 1 of 3i is just 3i, minus 3i times 1 would be 1 of minus 3i, minus 3i times plus 3i, minus 3 times plus 3 would be minus 9, I by I is I squared. If I add up my like terms, I have plus 3i minus 3i, and I also know I have to do my substitution, I squared is minus 1. So plus, they actually add up to 0, plus 3i minus 3i, I'd have 0 i's overall. So I'd have minus 9 times minus 1. So I would end up with 1 plus 9, so I would end up with 10. So I ended up with a purely real number. This isn't accidental. You might notice that I have 1 minus 3i, 1 plus 3i. This is called the complex conjugate. We are going to come back to it in just a moment. I'll write that in here. So again, we have, if this was our original number, 1 minus 3i, the complex conjugate of that number would be 1 plus 3i, and it's called z with a little bar on the top of it. And it turns out to be important because multiplying a complex number by its complex conjugate always gives you a real number. It gets rid of the imaginary part. It gives you a real number at the end. So it's something we want to watch out for in some types of problems. It's a tool that can be useful to us. Now another thing that can come up is this looks very similar to the question that we have here, but it isn't because there's no bracket. I write this in, there's no bracket around those two numbers. So the only part of this that is multiplied by my bracket is the minus 3i. So we need to be careful that we always read our questions, take a moment and make sure of what's being asked of us. So in this case, the only thing that is multiplied is the minus 3i. There's no brackets around that first section. So it's just the minus 3i that's multiplied. So just keep an eye out for that. This 6 is just going to come along until we've tidied things up. So we have minus 3i times 4 would be minus 12i. Minus 3i times 6i would be minus 18i squared. And I know I squared is minus 1. 6 minus 12i minus 18 minus 1. So I end up with 6 minus 12i plus 18. So I end up adding my real parts, my like terms, and I end up with 24 minus 12i because I put my real part first. Now we can also be told, we're also can be given names for complex numbers and then told what to do with them. So we could have z would be 4 plus 5i, and you'd have z bar would be 4 minus 5i. Again, this is an example of complex conjugate. What's changed is the sign of the imaginary part. That's what changed here as well. So if our original number was 1 minus 3i, then it becomes 1 plus 3i. If I started out with 4 plus 5i, then the sign here changes and I end up with 4 minus 5i. So how we can do this is we simply follow the instructions we're given. We're told what z is, we're told what z bar is, and we're told to multiply them. So we just do that. So we have z is 4 plus 5i, and we have z bar is 4 minus 5i, and because I recognize this is a complex conjugate, I'm expecting to get a real number as my answer. So I just multiply this out as I normally would. I have 4 of my second bracket plus 5i of my second bracket, and I write that out fully and follow all of my multiplying out rules that I would know for any algebraic bracket at all. So I end up with 4 times 4 is 16, and so on for multiplying out all of my parts. Minus 4 by minus 5i is going to be minus 20i. Plus 5i times 4 would be plus 20i. I can see my I parts are adding up to 0. And plus 5i minus 5i will give me minus 25i squared. And I see I squared, I know to convert it to minus 1 for doing my simplification. So I have my complex parts add up to 0, or my imaginary parts, I should say, add up to 0, and I'm left with 16 minus 25 times minus 1. So I end up with 16 plus 25. So I end up with 41. Again, a real number because I was multiplying my complex conjugates together. And all that happens for complex conjugate is I change the sign of my imaginary part. So we can see that multiplying out complex numbers is almost identical to normal algebraic multiplication, except that we have to keep an eye on where we end up with I squared and always do the substitution that I squared is the same as minus 1. And that is what we need for now.